Good morning, students. So today we'll discuss about the pseudo first order reaction and the chapter chemical kinetics. So pseudo first order reaction is basically a second order reaction, but it follows the first order kinetics. That means it's a second order reaction, but whatever the equations we have for the first order, it follows exactly the first order rate equations and integrated rate equations, etc. Okay, why? Because look at this reactions, okay, in which ester is decomposed into acetic acid and alcohol. Okay, so ester is decomposed in the presence of water to form this is carboxylic acid and alcohol. In this reaction, what we notice is that if t equals to 0, that is initial time, suppose the concentration of the solute is very small, so 0.01 molar, right? Then the concentration of water, because the reaction takes place in a water, so it has very large quantity, so I'll just write 10 mole, right? Then what is the amount of product? Initially it's 0 and 0 because the reaction has not yet been started, right? Then after some time, suppose time equals to t, if all this amount has been consumed, then the amount of this reactant will be 0, ester will be 0, and how much this will consume is 10 minus 0.01, right? Because according to this equation, it says one molecule of this ester reacts with one molecule of water to produce one molecule of this carboxylic acid, this is acetic acid here, and one molecule of alcohol. Here is ethanol, right? So if 0.01 mole is present initially, because this is solute present in a small quantity and this is solvent, right? Then if all the solute has been consumed, then here is 0.01 mole is also consumed. So how much is that? Yes, this gives 9.9 mole. Okay, to form the product is again here 0.01 mole of this one and 0.01 mole of this one. So if so ultimately the thing is, if the one of the reactant is present in a large amount, we can think that the concentration or the amount of that reactant practically remains unchanged, right? Practically remains unchanged. That means there is hardly any difference between 10 and 9.9. Okay, so because the amount of solvent is present in a very large quantity, right? So if we check the rate now, rate equation here, the rate is equals to, since it is a second order reaction, it depends on both the reactant CH3CO C2H5 to the power 1 and H2O to the power 1, so 1 plus 1, so this is a second order reaction. All right, this is just a k dash, okay, so don't get confused. I can write it as k1 also, fine. So this gives n equals to 2. But what happens in the whole process is, since one of the components is present in a very large amount, so we can say the amount of the water practically remains unchanged. Okay, so unchanged, so the concentration of water remains unchanged. That means it is a constant term. Now this constant and this constant we can together write as a k, okay, CH3CO C2H5 to the power 1. Now rate equals to, okay, since we can write k equals to k1 and H2O1, because this is also constant. Why? Concentration doesn't change because it's very present in a very large amount, so little bit of change and then its concentration practically remains any difference, okay, practically makes any difference. So look at now this equation. Now this equation is a first order reaction because the power is 1 here, total power is 1, right? So when the one of the reactant is present in a very large amount, then even if it is a second order reaction, but it exactly follows the first order kinetics. So the next topic is temperature dependence of the rate of a reaction. Now, how temperatures depend on the rate of a reaction. So according to the Arrhenius equation, it says that K, that is a rate constant, is equals to A e to the power minus EA by RT. A is here is called Arrhenius factor or the frequency factor, and it's basically a constant. E is exponential to the power EA. EA is the activation energy divided by RT. R is a gas constant, T is the absolute temperature. So this equation gives the relationship between the rate, basically the rate constant, with the temperature. Okay, rate constant means it also depends on the rate. So you can also say that the rate, this equation gives the dependence of the rate versus time. Okay, now looking at this equations, H2 plus I2 gives 2 of HI. Okay, so if you plot the reaction progress of this reaction, so this is called reaction coordinate. Reaction coordinate, that means the reaction as progress, and here we write as a potential energy. Potential energy. Now if you plot the graph here, it is an exothermic reaction, so the graph will be something like this. Okay, so this is the total energy possessed by H2 plus I2, and this is the energy possessed by these two molecules of HI. Right, now this much height is the energy of the reactant, and this much height is the energy of the product. Now what will be this is the difference between the energy of the reactant by energy of the product. So this is known as delta H. Now delta H is the heat of enthalpy that is released. Okay, energy released, because reactant has a higher energy and product has a lesser energy. So that means this amount of energy has been released. So looking at the graph, we can say this is an exothermic process. Now if we measure this height, this is called hump. Okay, this is called EA. It's called activation energy. Now what is activation energy? Activation energy is the minimum energy that must be supplied to the reactant to undergo a reaction. And how much, what is this whole from here, from 0 to here, this is known as threshold energy. Okay, E T, we'll just write ET. ET is the threshold energy. From here to here is the threshold energy, because the reactant must possess some extra energy, that is activation energy, to acquire a minimum to attain this hump. Okay, potential barrier, technically term we call it potential barrier, to cross this reaction. So reaction it has to cross this potential barrier. Okay, the height of the potential barrier from the reactant is known as activation energy. Okay, so what is this can be written as a ER, that is energy produced by the reactant. So what is EA? So EA, mathematically we can write EA is equals to ET minus ER, right? So activation energy is the so, threshold energy subtracted by energy of the reactant. Okay, so this is the energy barrier, potential barrier, energy barrier, and this is activation and complex. So first the reactant A plus B or H2 plus I2, then it forms the activity complex, then it forms the product. Here is another graph. It shows the temperature dependence of a rate constant, rate of a reaction. So here what we have noticed is that, so okay, I'll just talk about this is the kinetic energy, right? Ke, this side, and this is the fraction of the molecules, that is Ne by Nt. Ne is the total number of molecules possessing the energy E, and Nt is the total number of molecules, and E is the number of molecules possessing energy E, and T is the total number of molecules, right? Suppose uh, now at particular temperatures, suppose we can write T. Okay, we obtain this type of graph, right? So here is the EA. EA means activation energy. Okay, So all the molecules which crosses this activation energy can undergo the can form the product, right? So you can see this is the first we'll look at this curve. See, so all the molecules which cross this potential energy, this kinetic energy, okay, so this undergoes a reaction. So this molecules undergoes reaction, and all the molecules here does not undergo reaction because it does not have sufficient kinetic energy to form the product. Okay, according to the collision theory, it says that the molecule must collide simultaneously to undergo a reaction, right? But it must have a sufficient energy. Okay, it must have some minimum energy to collide. Otherwise, the ordinary collision doesn't result in the formation of product. So this much. Now again, what we did is we raise the temperature by 10 degree. Okay, so T plus 10. So the curve has been a little bit flattened now. You can see with the rise in the same, all the conditions are same, okay, except the rise in 10 degree Celsius or 10 Kelvin. So the curve has been more flattened. So what we have observed is that now the more number of molecules, you can see the area here, the more number of molecules now undergoing the reaction, that is more number of product has been formed. So it has been if you see the clearly this one, the area or initial area is this much, and after the rise in 10 degrees Celsius that area is this much, right? So it has been observed that with the rise in 10 degree, the rate of the reaction is nearly doubled. Okay, with the help of this graph we can say that the with the rise in 10 degrees Celsius or 10 Kelvin, the rate of the reaction is nearly double. Okay, earlier we have said that this is the Arrhenius equation. Rate constant K equals to Arrhenius constant e to the power minus Ea by RT. Ea is the activation energy, R is the gas constant, T is the absolute temperature. Now what we'll do, we'll just do a little bit of derivation from here. So taking log on both sides, taking log, that is natural log on both sides, we get, okay, so ln k is equals to ln a e to the power minus ea by rt. Fine. Okay, I'll just put the bracket. So this can be written as a ln a, okay, plus ln e to the power minus ea by rt. We know the theorem, and we know the law, that is ln x into y. Okay, ln x into y can be written as ln x plus ln y. This is the properties of logarithm. Again, this can be written as ln minus e a by rt. Since there is another property, it says that ln e to the power x can be written as x. ln e to the power x, this is natural log, okay, with the base evens. So e to the power x can be written as x. So everything power is comes as a here ea by rt. Fine. Okay, so here is a ln k. Oh sorry, I messed up this ln a. Now we'll just rearrange this one. ln k is equals to minus ea by rt plus ln a. Fine. So we'll put it this as a equation 1. Now we'll just look at this equation. Is ln k is a constant, so everything is a constant. Here ea is activation energy, so it remains same for a particular reaction, and r is a gas constant obviously, and a is a Arrhenius constant, so ln a is a constant term. So only the two variable here is, oh sorry, with the rise in temperature the rate constant it changes, we have already talked. So this k is a variable here and t is a variable here. Okay, with the rise in temperature rate constant or the rate of the reaction changes, so these two factors will change. So we'll just write at t is equals to t1, we can say we have k equals to, we'll just write k1. Then we'll substitute this value here. What we get is ln k1 is equals to minus EA by R T1 plus ln A. Fine. So this is your equation 1. Equation 2. Similarly, at t equals to T2 we have k, small letter k, is equals to K2. K2. Then we'll substitute this one. So equation 1 implies ln K2 is equals to minus EA by R T2 plus ln A. Right, so this is your equation 3. Now we'll subtract this equation 1, equation 2, this equation from this equation. So by subtracting equation 2 from equation 3, we get, so just keep this in front, minus ln K1 is equals to this minus EA by RT2 plus ln A minus everything this comes minus EA by RT plus ln A. This is T1, this is T1. Okay, so we'll just open it. EA by RT2 minus ln, sorry, plus ln A minus, so minus minus is plus, so EA by RT1 minus E, sorry, ln A. So ln A is cancel, minus ln A. So what it remains is, we can take the common from here also, EA by R. Okay, we'll take it common. That's EA by R. We'll take, so this is a positive sum, 1 by T1. Here comes minus 1 by T2. So here also we can write is a ln, it's a K2 by K1. Fine. So what we ultimately get is ln K2 by K1 can be written as this equation. So equation 4. And this is a very important equation. Now we'll just change this ln with log. Now this one, this means it's a log K2 by K1 is equals to EA by R 1 by T1 minus 1 by T2. Log means 2.303, it comes here. Okay, so we'll keep this here. So log K2 by K1 is equals to EA by 2.303 R 1 by, we'll just multiply it. Okay, this LCM is T1 T2, so here comes T2 minus T1. Right, so this is the equation, and this one is also very important equation.